Hello friends, welcome you all to the next lecture of GCE Connect series. In today's lecture, we'll be starting with module 4 with the topic Centroid. Let's start with the definition. Centroid or center of gravity. Center of gravity is that point where the entire weight of a body is assumed to be concentrated. It is denoted by Cg or G. So, what is center of gravity? For any mass or a body, for analysis, we assume that the entire weight of the body is transferred through one single point, which we term it as center of gravity. It is denoted by G or Cg. Further, if we have a laminar figure which doesn't have a mass but it has an area, the term center of gravity is termed as centroid in that case. So we define centroid as it is the point where whole area of a plane figure or a lamina is said to be concentrated. For example, now if I take an object such as a duster, for the duster we'll name the point as center of gravity because it has a considerable mass. Whereas if we take a piece of paper, say a A4 sheet if we take, it has very negligible mass but a considerable area. So it is a form of a plane lamina or a plane figure. Now for that paper, we'll term the point as centroid. That is the basic difference. So let's come to the axis of symmetry. In case of symmetrical figures like rectangle, square or circle, the figure can be divided into exactly equal portions along the axis, which is known as axis of symmetry. Yes, this is the axis which divides the figure into exact equal parts. For example, if we take a rectangular paper and if you want to divide the paper or cut the paper into two parts, what we do? We fold it. We fold it and at the fold we cut that paper. So in this case the fold which we have made is nothing but the axis of symmetry, because along that fold when we cut we have two parts of a paper. Secondly, I'll take a common example of a lemon. If we want to cut a lemon in the kitchen, we cut it such that we get two equal halves of the lemon. So the axis along which we are cutting nothing but is the axis of symmetry. So we can get two types of figures. One is which we have symmetry along both the axes. Example, if I take a circle, if I draw a horizontal diameter, the diameter becomes an symmetrical axis, because if I cut along the diameter, I'll get two equal parts. Similarly, if I consider the vertical diameter as an symmetrical axis, if I cut along the vertical, again the circle is divided into two equal parts. So this is a completely symmetrical figure where along both the axes when we cut the figure, it results into equal halves. Now whereas if I take an equilateral triangle, okay, imagine an equilateral triangle. If I cut that equilateral triangle vertically, left and right side will be the same. Okay, whereas if I cut that equilateral triangle horizontally, the top and bottom won't be same. So we can say that this triangle, equilateral triangle, is symmetrical only about one axis, that is vertical axis, and it is not symmetrical about horizontal axis. The figures like square, rectangle, circle are symmetrical along both the axes, whereas we get some figures which are symmetrical only about one axis, and third category of the figures is such that they are not symmetrical either about x nor about y axis. Now if we take alphabet I, if we cut I letter vertically, left and right will be the same. Even if we cut horizontally, top and bottom will be the same. Whereas if we take an alphabet T, T for tiger, if we take an alphabet T, if we cut the T vertically from the center, left and right are the same. But if the same cut we make it horizontally, the top portion and the bottom portion of the alphabet T won't be the same. This is what is symmetry and axis of symmetry. Next comes the centroidal axis. It is that axis which passes through the centroid or center of gravity of the figure. Now for symmetrical axis, axis of symmetry and the symmetrical axis overlap. Okay, axis of centroidal axis and axis of symmetry overlap because both are same. Next is axis of reference. It is any general axis or standard axis which is taken as reference. Now we have our x-axis, y-axis which we use commonly while drawing a graph. They are a reference axis. With respect to it, we can locate the centroid or center of gravity of a figure. Now this sketch here which I have put is just an example where we can recognize the different axes. Now your x and y axis are your standard axis, which are your axis of reference. Now CG, which is marked and shown in green color, is your centroidal axis. Now the figure taken is rectangle in shape. That means it's a symmetrical figure about both vertical as well as horizontal axis. Hence, in this case, the axis of symmetry coincide with the centroidal axis. Okay, that means that both are same. So here if we want to locate the center of gravity, that is the C point which is shown on the figure, you can locate it with respect to x-axis, that is the finding the vertical distance, which we term it as x bar, or you can locate it with respect to y-axis also by finding the horizontal distance, okay, which we term as x bar. So basically the coordinates of your centroid are x bar and y bar. Okay, so that is what we need to find in this chapter, locating CG of the given figures. So now let's come to the formula by which we can locate the CG. For symmetrical figures it is very easy because the center itself is the CG. But when we have unsymmetrical figures or plane laminars, how can we locate the CG? This derivation will give you the idea for it. Now let us consider an body which is having a total area A, capital A. Let x bar and y bar be the coordinates of the CG of the entire body. Okay, clear? Now let us divide that body into small elements, each of area say A1, A2, A3, so on up to AN, such that their centroidal distances from the axis are x1, x2, x3, so on up to xn, and y1, y2, y3, so on up to yn. That means the entire area A is divided into small elemental areas A1, A2, A3, such that if we add all the small elemental areas, we'll get the same area, capital A. Now, in this case, our task is to find x bar and y bar. So, applying the theorem of moment about y-axis and x-axis, we get A into x bar is equal to A1x1 plus A2x2 plus A3x3, so on up to AN xn. Now what is this theorem of moments for an area is, A is the entire area, whereas x bar is the centroidal distance of the entire area. So it can be written as what? We'll take an individual element and multiply it with the x value for that particular element. And when we do the summation of all that, the equation which we get is A into x bar, that is the total area multiplied by the centroidal distance, is equal to an individual area multiplied by its centroidal distance, and summation of such gives us x bar. So in the below formula, if we cross multiply, summation of Ax is nothing but A1 x1, A2 x2, so on. A is shifted to the right hand side, it goes to the denominator, and we get the formula for x bar as summation of Ax divided by A, where summation of Ax is A1 x1 plus A2 x2 plus A3 x3 and so on, whereas capital A is the summation of entire area or the total area. Similarly, we'll get y bar as a into y bar is equal to summation of ay, that is summation of ay is a1 y1 plus a2 y2 a3 y3 so on, divided by a, which is the total area. Or if you want to write it in the form of integration, which we require to use during our derivations, we can write integration of x dA upon a is x bar, whereas integration of y dA upon a is y bar. Here what is dA? dA is a elemental area in x direction, and dA multiplied by y is the elemental area along the y direction. So the second integration formula which we have noted here is further used in the derivations. So this is an important relationship, please note it down. Now let's come to the last concept of today's class, that is by using the formula which we derived in the previous equation, let's find or let's try to locate the centroid of a triangle. Now in this case here I have taken an right angled triangle ABC. I want to locate the centroid of it. Now see the figure. If you cut it horizontally also, it is not symmetrical, or even if you cut vertically also, it is not symmetrical. That means that we will get the value of both x bar as well as y bar. Okay, keep this point in mind. If the figure is not symmetrical about both the axes, we need to find both x bar as well as y bar. Whereas now if you would have taken a rectangle instead of a triangle, rectangle is symmetrical about both the axes, therefore its centroid itself the center. That is, if the height of the rectangle was h and width was b, then we would have got the centroid directly as b by 2 and h by 2. But here in case of this triangle, it is not that case, so we need to derive it. So let's start with the derivation. Consider a triangle ABC. Okay, then it has a height h and the base BC is small b. For analysis, we will take an elemental figure which has a width of b1, okay, and the height of that element will be h minus y, because that element is located at a distance of y from the bottom, so the height will be h minus y. So now here in this figure we get two triangles. One is our main triangle ABC, second triangle is AEF, which we have got by taking an element which has a thickness or a depth of dy. Okay, hope the figure is clear. It is straightforward. Then further, let's find the value of b1. Okay, let's find the value of b1. We'll use the principle of similar triangles. Make a note, here we are applying the principle of similar triangles. The two similar triangles considered here are AEF and ABC. So let us take the ratio of its sides. b1 upon b is equal to height of the smaller triangle as told is h minus y, whereas height of the bigger triangle is h. So by cross multiplication we get b1 as 1 minus y by h into b. So this is the value of b1. Therefore, what will be the area of that element? As it is a very small element, let us consider it as a rectangle. The area of the rectangle is breadth into depth. Here breadth is b1 and depth or thickness of that elemental strip is dy. Therefore, the area of the elemental strip, as it is an elemental strip, we are taking it as dA. dA is equal to b1 into dy. So b1 value we have found on the top, substitute it, that is b1 is 1 minus y by h into b into dy. Now area of a triangle, this formula is half base into height. So from the principle of moments, what we have got is y bar is equal to integration of y into dA upon a. Okay, that we have derived it earlier. Now in this a value we know directly that is half base into height. So let us find integration of y into dA. So as we have taken the strip horizontal, the limits will be from 0 to h. Okay, the limits will be from 0 to h. So substituting the value of dA, y into dA dy and integrating it, you know integration better, we get the answer as bh square by 6. So integration of y into dA comes out to be bh square by 6. So here why we have taken h is we are locating the element in the horizontal direction and its height is taken with respect to the bottom or the base of the triangle. Hence we are taking the variations along the height of the triangle, which varies from 0 at the base to h at the top. Hence our integration limits become 0 to h. Therefore substituting, we get y bar is equal to b square by 6 into the area. First of all we apply the limit 0 to h and then substitute it and get the value of y bar. Solving, we get y bar as h by 3. What does that mean? From the base of your triangle, the y bar lies at what height? H by 3. That means, say for example, if the height of the triangle is 6 meters, your y bar, that is the centroid from the base, will lie at what height? 6 divided by 3, which will get as 2 meters. Okay, so from the base y bar is 2 meters. Similarly, if you want to locate y bar from the vertical side of the right angle triangle, it will come as b by 3. Okay, it will come as b by 3, whereas when you locate from the base, it will come as h by 3. Therefore, the centroid of the triangle, you can write it as CG is equal to x bar comma y bar. X bar is similarly when you derive, you will get the answer b by 3, or and for y bar you will get the answer h by 3. Okay, so in the next class I will give you the other triangles or the formula list, need not worry. If you have an equilateral triangle, say of side 5, okay, 5 meters each, side is 5 meters, then in that case what will be your CG? As equilateral triangle is symmetrical about vertical axis, directly you will get x bar as 5 by 2, that is 2.5, whereas y bar will be h by 3, that is 5 divided by 3. This is how we need to find the CG of different figures. So in the further classes, I will take up figures such as a semicircle, a quarter circle, which are very important. Okay, go through this video. If you have any doubts, please get back. Thank you, one and all.